Hello everyone, and welcome to another day of pre-calculus review. Today, our agenda will be to cover the parabolas out of the three types of conic sections. Well, we were introduced conic sections the last class and then worked on the concept of ellipses the last class. We're still going to go over the entire concept each time to make sure that you understand this basic concept. Because it's essential that you understand that what conic sections fundamentally are, so that you can apply that knowledge in word problems. So, for a conic section, you have, oh, sorry, you have two cones. You have two cones. One of them is like more or less lying on the corners of each other, and for a conic section, just like the name says, you take a section of the circle. You take a section of this 3D square. So if you were to cut this square in any way, say we cut it horizontally around here, the cut, the two-dimensional cut would look something like this, right? It would be something pretty close to a two-dimensional circle. Maybe a bit deformed if it wasn't completely horizontal, but more or less more or less pretty shaped. What if we cut it like here? This is a bit harder, but if you think through it, well, this tip at the end makes something like this here, and same goes for here. So this would form a type of a hyperbola, and this forms a weird kind of ellipse. If you cut that part of a cone right there, so understanding these, we went over ellipses, right? We said that in the problems that we looked over in the last class, we said that ellipses were commonly used in stuff for like uh domes and bridges because of their special quality. Uh, you know how they have two foci, right? And like if you draw a line to the edge from the two foci, this total distance is always equal no matter where you draw to on this circle. Foci and uh, other conic sections play a type of a similar rule. So today we're going to be going over what exactly uh, the parabola is. So outside of conic sections, you've probably heard of what a parabola is before. I mean, it's just this, right? On a xy plane. And the equation looks something like y equals x squared plus 2. Really simple, right? And you might be thinking, well, this feels like pretty different from a conic section. Like, you don't need a y squared plus x squared and that stuff. So you might think that, I'm not sure if this is actually conic section. But here's the thing. So, what is like a parabola shaped like? It's shaped like it's shaped like a sort of like opening U, but there's like a specific pattern to this curve, right? This curve isn't just decided randomly, depending on like whatever whatever distance that you put in. No, depending on how depending on the curve, each parabola has a foci. It's a single point here and not two, but there is a singular point of foci and a directrix line. So for this equation, it would look something like draw this in red. It would look something like that. Now, what are these lines for? Well, essentially, the foci and the directrix are drawn at the point where the distance from the graph at that x value to the foci to straight downwards to the line of the directrix are equal. So, most importantly, we draw this here. Let's say this is a distance of 1, right? Between this graph here and where the foci is. Then the distance between 0, the directrix, and 1 must be 1 as well. If we were to talk about something here, this what x value right here, this distance to there must be equal to the distance that you draw to the foci from there. This is the same no matter where you're talking about, even if you're talking about here all the way where the parabola extends. If you drew a line back to the foci, you get the same answer. This explains why the shape of parabolas tend to curve out, like tend to change more drastically in the beginning, and tend to flatten out as they get out further, because it's based on a distance to a point, the similarity of a distance to a point. So essentially, the longer you get, the less different the variation will be, essentially. So now, let's look at what the base equation of a parabola should look like. Generally, parabolas tend to come in equations that look something like y equals a times x minus h squared plus k. This is generally the equation. What y means, well, it's y in the case that it's being drawn on the y-axis, and the parabola is not horizontal. It extends up or down, upwards, depending on if a is positive or negative. And as always, h and k generally stand for the coordinate, where you put them on, and just like usual, what you put in here is negative h, so don't forget to take the opposite of what you put it here and put it into the x value. So you plug that in, and well, probably the most important point about uh, the parabola is the value of a. Now, we talked about these foci earlier, right? So you might be asking, well, how are we supposed to find out where the foci exist? So to give you the answer, the equation of the graph of the equation to figure out the coordinates of the foci point are h comma k plus 1 over 4a. And this is the point of the vertex. You can see the only difference on here is the value of a, right? This value that you add of 1 over 4a. In some ways, it makes sense. Because, well, obviously, if the value of a is positive, that means that parabola will be opening upwards, so the foci point will be located somewhere like here, above the graph. If a was negative, that would make this adding of 1 over 4 a negative. So you would have this point, vertex point here, and have the foci here, which means that the entire rest of the graph needs to be drawn negatively, because in order to match the directrix. And in this case, remember how we gave that rule of the directrix having to match the distance? Well, we take the difference of this y value, essentially 1, 4a, which is the difference between the vertex and the foci, then we subtract it by here and draw a straight line through it. So this point is technically k minus 1 over 4a. And using this, we kind of figure out what to do. Let's look at how this rule applies with different transformations. So k plus 1 over 4a, right? What does this mean if a was to be bigger? What would happen to a parabola if the a value was bigger? Which means that the foci was located farther away from the rest of the graph. Let's not draw the graph here, assuming this is the vertex. This whole line is the directrix. And this is the foci. This is the vertex and this is the foci. Meanwhile, on another graph, say this is the vertex, this is the foci, and this is the directrix. Let's try drawing these out. You can technically draw a graph without actually having to plug in any values. So same distance, find here. You need to find the point where this and this would have the same distance, which you assume to be there. Here and here, here and here. Looks kind of something like this, pretty wide, right? In this case, well, pretty far. Now, in this case, because the foci is further away, the central focus, which means that the point at which it begins to the parabola begins to narrow down is a lot steeper than what this one where the foci is close. This means that the higher the value of a is, the more narrow it is, no matter whether it's positive or negative. Because in this case, graph looks something like this. Let's try some problems about this then. Let's first start by graphing some parabolas. So let's say we get a random parabola, y equals 2, negative 2 of x minus 1 squared. Let's try graphing this. Zoom out, move down. So before doing anything, figure out the vertex. The vertex of this will be on 1, comma 0. We know this because this is x minus 1, and h is 1, making it negative 1 here. Next, we figure out where the foci is located. Uh, Using the same equation, well, we know the x value is the same, but for the y value, what is a? Negative 2, right? A equals negative 2, and the equation for this is 1 over 4a, which means 1 over negative 8. You add 8 to this, which means that, so you subtract 0 by negative 1 over 8. So the dimension for this becomes 1 comma negative 1 over 8. Graph of this. 1. This is the vertex, and this is where the foci is. So using the same logic, the distance between the foci and the vertex should be equal to the distance, the shortest distance from the directrix to the vertex. So this would be positive 1 over 8 here. This whole line this whole line becomes more or less the directrix. Drawing the graph here, we do this. If we were to draw something like here, it goes like this. Yep, and on, and on, and on. Just looks something like this, and it goes on permanently. And it's actually really simple. Parabolas require a ridiculously little amount of information in order to complete the graph. Although it may not be precise, you can technically figure out how a parabola is meant to be graphed by understanding where by being just given 2 points. Of course, well, like you could technically draw the ellipse using the 2 points of the foci. It's a lot more simpler and more easily visualizable in the case of parabolas. Let's look at some variations of what you might see for parabolas. So first, what if you get a parabola that looks like this? And that's not like a plane trick. This plane is x and this plane is y. Well, you might go like, hey, wait a minute, what? This doesn't pass the vertical line test. It's not a function. Well, yeah, you might be true, because in this case, it's not a function of f. I mean, it's not a function of y, it's a function of x. The equation for something like this, instead of having been y equals a x minus h squared plus k, uh, instead of this, it's x equals a of y minus h squared plus k. See how the x and y are switched? This effectively flips, uh, rotates the graph by 90 degrees. Everything else is the same. Like, because it's y negative h of here, the value of this is pushed here instead of that. Oh, and one thing to understand is that generally the h and k values are more or less reversed. So instead of putting h for the x value, because h is directly affecting the y value, it will you would find the coordinates of the vertex using kh instead of h comma k. So this is something to watch out for. And in some problems, they might want you to make the same parabola, except just rotated. In that case, you just draw it, draw out the y parabola and try to understand the distances between the foci and the directrix and replicate that, except that you just do it vertically. It's not too hard. What about what are some word problems that you might see used? Well, like we said before, we saw ellipses used for bridges and used for domes, right? Well, parabolas are often used for dishes, as in not like dishes to eat food or things, but a radio dish. Let's try drawing it. You ever seen those things like hanging out the roof of someone? They look something like this. Yeah, it's like a cup kind of, and then they have like this middle antenna sticking out in the middle. It's just like round in there. You probably have seen it. The reason this needs to be of a parabola is you see this dot here, right? Well, this antenna is essentially the foci of the point because the same rules follow. No matter where the waves come, they bounce on the dish and are able to reach the central antenna. That is the goal of why you would use a parabola to, to construct a satellite dish. That's why a satellite dish is not just like flat. They would just bounce off elsewhere. If you made it rounded in the shape of a parabola,
Let's say it bounces here, then it goes here, it hits here, goes here. Let's say it goes here, it hits here. Whatever you do, it all reaches like the central axis. Now, in most problems you get, you will assume that the tip of the antenna is generally the foci of the parabola. So let's say you get a word problem. Word problem says, word problem says, dish. The uh the dish is located on top of someone's roof. The distance of the base of the dish, right here, to the tip of the antenna is 50. Write out the equation to this write out the equation to this parabola, assuming that the base of the dish starts at 0, comma 0. So to do this, well, you know that the gap here is a whole 50, right? Then this means that 1 over 4a equals 50. Multiply this out. 1 equals 200a. So a equals 1 over 200. Yeah. So assuming we do that, I equals 1 over 200 x squared is the answer to how you would solve this. Is that right? Hmm. Oh, oh. Give me a second. Yeah, yeah, yeah. This is right. So, essentially, all the information we got was the distance between the vertex and the foci, right? But using that, we could figure out the entire equation. So, main point of this was all you need to figure things out are just the coordinates of the vertex and the foci. Those are the only two things that you need. Hmm. Hmm. We do have a little bit time left over. So look at some let's begin like some interactions over how parabolas are related to hyperbolas. Essentially, they're a similar concept, except that there's two U's instead of one. By the way, we're gonna go over this at the same thing at the beginning of next class, so you shouldn't be worried if you don't get it right now. We're gonna go over it again, and I'm gonna go over it in more detail. Main point is, how we had a foci and a directrix now? Well, essentially, we have another graph to take care of it. So using this, we have a foci for the top part and a foci for the bottom part. And the half line between the hyperbolas essentially acts similar to the directrix. That's that. And remember, these two fundamentally can't be that different because back on the cone, the difference was that the parabola only crosses over one cone. It just extends at a slightly different angle to where it crosses over both cones. So fundamentally, they are not too different. I think that will be it for today, and thank you for watching, and have a great night.